Hi, my name is Calvin, the designer for Group 6. Australia, of course, was built by gold mining of the 1850s, and this story is not new. Since it was first discovered 40,000 years ago, many empires have been built by mining, such as the Spanish, Romans, and the Phoenicians. Even now, our green tech revolution is dependent on a few sources of cobalt mines in the Congo. Despite how mining has created great wealth for many, it's also a bane for many other people as well. Access to mines and the requirement to source cheap materials have led to wars, slavery, child exploitation, and the division between people. Even today, our green tech revolution depends on a few cobalt mines in the Congo. We as a team have lineages across the world, and while we acknowledge that this Mars project is merely a first-year project, we sincerely hope that one day, just like our team, humans from all over the world will come together and create this into reality. So we will finally see a change after 40,000 years of suffering and exploitation.
Problem definition is the first phase in Clive Toon's perspective model of the engineering design process, in which engineers develop a problem statement that details customer requirements, clarifies the objective, identifies constraints, and establishes functions of the design. The problem definition is an essential means of determining the parameters of the task at hand, since often the initial statement can be vague or easily misinterpreted from what the client actually intended. It is the engineer's responsibility to clarify the objectives of a task before any concept generation or testing of solutions begin, in order to avoid wasting the time and resources of both parties. Developing a formal problem statement ensures that every constraint is identified, as many factors such as time and cost can easily be overlooked if designers skip straight to focus on generating ideas that may turn out not to be feasible. Finally, a project statement can be used to help articulate the required functions of a design, which lead directly into the second phase of the engineering design process, concept generation. This gives specific direction to the design and clearly establishes the goals required to achieve the task.
So in working on our problem statement, our group aimed to produce a statement that was short, concise, and unambiguous, and free from unnecessary constraints or restrictions on design and or function. In order to achieve this, we split our approach into 3 steps. First step was to perform an initial problem definition, as defined by Dim, Orwin, and Little. This was discussed by Ronan. Part 2 was understanding a bit of background context as to our problem. And finally, the third was to go through the 5 W's for our problem framing. So completing the 3 steps that I just discussed yielded the initial problem statement that you can see on your screen, which will be broken down further in the next few slides. So firstly, understanding the context. To help us better understand the environment and the context of the problem, we looked at publications that discuss the difficulties of colonizing Mars, as well as the dangers and opportunities presented by such a venture. A number of publications discussed hostility of Mars towards humans. They highlighted aspects like temperature fluctuations, a thin atmosphere made up primarily of CO2 with no natural radiation shielding, as well as toxic levels of perchlorate in the Martian soil. There was a number of publications that also discussed the difficulty of establishing a colony there. The main points brought up were the distance of Earth from Mars, the fact that Mars has 1/3 of Earth's gravity, and that the Martian terrain is often unfamiliar and often changing. Several organizations, namely NASA and the Mars Society, also highlighted that Mars has several natural occurring resources that can be used by a human colony. These includes things like water locked up as ice, which can be used to create fuel, breathable air, and also drinking water. And also the Martian soil contains elements iron, zinc, and aluminum, which can be used as raw materials, and 3D printing a key infrastructure to help support and protect colonists. In framing our problem using the 5 W's, the who in our problem statement is not just humanity, but rather specifically we're dealing with a special group of humans who are looking to colonize Mars and establish a self-sustaining colony on the red planet. The where, quite simply, Mars. Although our initial prototype testing will be done on Earth, all prototype specifications will be such that optimal performance on Mars is the key consideration. The what. Our what describes our plan of attack. Namely to design, build, and test a rover that is capable of functioning on Mars to help humanity complete a task that is considered key to future human habitability on the planet. This is the safe and reliable return of natural resources to a 3D printer to be used in situ. Our in looking at our what framing, we try to avoid including any implied solutions to the problem. The why builds on from our background context, and it establishes that we're building this rover to give humans on Mars a safe and reliable method of collecting the abundant resources Mars has available indigenously. In achieving this, we're actually making it easier for humans to build radiation shielding and life support infrastructure, which is absolutely crucial for a long-term stay colony.
The purpose of the conceptual design phase is to create a model that translates the functional requirements and objectives established from the problem definition phase into working principles and physical solutions. This is important as it formally identifies design opportunities and generates a collection of models that give a feel for the problem at hand, enough to provide a basic understanding of how the product will behave prior to building it. Such models are generated by creating a design space, an intellectual region of design alternatives that contains all the possible solutions to the design problem. An example of a tool used to create a design space is a morphological chart. A morphological chart allows engineers to visualize a large range of physical solutions to specific functions and quickly create multiple designs by using different combinations. Design spaces are crucial as they allow engineers to consider a range of perspectives from peers, facilitate innovation, and increase opportunities for realizing the most feasible solutions. In this case, the California Institute of Technology reinforces that quantity yields quality as it leads to more creative design solutions. Additionally, due to modification costs during the design phase being low, refining models during this process reduces development costs as it prevents engineers from having to make late design changes, which drives higher costs. A survey by a design software firm, PTC, found that a high proportion of development costs are committed at the conceptual design phase. 43% of this survey claim that 71% of the total product cost is fixed by the time they complete the conceptual design phase. Thus, the conceptual design phase is important as it facilitates innovation, outputs a feasible solution, and effectively reduces unnecessary expensive costs that may arise in the later phases of the design process.
Currently, our group has come up with 3 unique and promising concepts that combine the best features compared to the morphological chart, each with their own benefits and drawbacks. Our first design features a bucket collection system, a plywood chassis, a 4-wheel configuration with front-wheel steering, and a hinged open box bed for storing and depositing the samples. The benefit of this design is its simplicity and affordability due to the use of cost-effective materials such as plywood. It also features previously proven and reliable systems such as the excavator-style bucket and the open box, which also provides easy access for depositing the collected samples. However, this design lacks in innovation and is also limited by its earth-centered design. The open box may cause material to fall out while being transported across bumpy terrain, and the use of a 4-wheel system may limit the rover's maneuverability on Mars' surface. Design 2 features a conveyor belt collection system, an aluminium chassis, a track configuration that utilizes skid steering, and a slanted box with a hinged door for storage and deposit. The benefit of this design is its efficiency in collecting samples. The conveyor belt can continuously collect a large amount of samples autonomously, and the track configuration with skid steering provides excellent mobility on a Mars-like terrain with a reduced amount of components. The slanted box also ensures the collected samples are secure during transport, an advantage over the open box of Design 1. However, the downside of this design is the high cost due to the use of aluminium and the complexity of the tracks and conveyor, which may require more maintenance and skill to implement. Design 3 features a collection system that uses a ramp and spinning paddle wheel to move the samples, a chassis made of 3D printed plastic, a 6-wheeled rocker bogie system with front and rear steering motors, and the same slanted box storage system. The benefit of this design is its versatility. The paddle wheel can collect samples effectively and autonomously. The 6-wheel rocker bogie configuration provides excellent mobility on rough and steep terrain, and the front and rear steering motors offers precise control over the rover. Additionally, 3D printing allows for custom design and rapid prototyping, which reduce the cost and time of development. However, the downside of this design is the complexity of the rocker bogie, as well as the paddle wheel, which may require more maintenance and will be more prone to failure. In conclusion, each design has its benefits and drawbacks. Design 1 is simple and cost-effective, but may not be effective in collecting samples in rougher terrains. Design 2 is efficient in collecting samples, but is expensive and more complex. Design 3 is versatile and customizable, but is more complex and may require more maintenance. Further testing, analysis, and decision-making will have to be conducted in order to choose a final prototype.
In order to create our designs, we utilized 3 main methods. The most prevalent technique used during our in-person meetings was a modified approach to brainstorming, where one or more group members would voice a Rover concept and would either be responded with acceptance, in which we would continue to build upon the idea, or rejected after some discussion about feasibility or complexity. This worked very well in developing baseline ideas, such as the type of maneuvering system that would be used, including wheels or tracks, and the resource collecting system, such as conveyor belts and buckets. Another technique we used is the morphological chart, which we divided into 5 components and have illustrated a multitude of ideas as to how to approach different areas. These include the maneuvering system, method of collection, and cargo compartment design. The chart served as a design dump in which everyone was able to consolidate their ideas into a single table for each of the individual components of the rover. This, in combination with our version of brainstorming, would later assist in consolidating various design ideas and forming them into a few final concepts. The final technique utilized was a modification of the Crazy 8, where each member of the team would independently create and present at least 3 rover designs. With a deadline of about a day, we were given ample time to produce multiple annotated designs. As with the advantage of the original Crazy 8's method, it allows for every group member to produce the same amount of designs, where everyone contributes. Furthermore, the frequency of certain components could be measured, with ideas such as positioning the resource container on the top of the rover, tracks and 6 wheels making a frequent occurrence, and conveyor belts and buckets being the most popular resource collection choices. These designs are also likely to be consolidated into the final concept designs, while also being more fleshed out and developed compared to the ideas generated in the previous 2 design methods. They also serve as the foundation of the final designs, which can be easily modified and combined with the other ideas that were created. In addition to these design techniques, we also utilized tools such as research and physics knowledge in producing some of the designs. The concepts for the 6-wheel rocker bogie suspension were inspired by a conference piece at Kennesaw State University, along with previous and currently operated Mars rovers such as Opportunity, Curiosity, and Perseverance. Physics knowledge was also utilized in conceptualizing a ramped floor for the resource container, as the force parallel to the slope is mg sine theta. By making the slope angle great enough, the resources would eventually pour out when the doors of the container are opened without any external influence.
The advancement of technology has been the driving element for humankind's demand for rare earth metals in the first place, creating a flotilla of supply issues amongst many others. With ever more countries opting to phase out all combustion-powered transport by 2050, we need to find solutions and continue our work in mining for these resources, but in conjunction with response to uncontrollable growth in the human population, there has been a strong push in finding the solution for both in space, the final frontier. A human colony on Mars is on cards for becoming a reality in the foreseeable future, with many space agencies sanctioning research for various solutions if this comes to fruition, with one being for a collection and transport rover. Our team has been tasked with producing a special collection and transportation rover that will collect and transport resources such as metals to the location of a future Mars base to be refined and used in the construction of a habitable base to house future human colonies on the Red Planet. Several draft rover concepts have been produced by our team, each with an emphasis on a separate collection mechanism. They say you can only test the skill of a fighter pilot outside the flight simulator. Likewise, Team 6's next steps will be on analyzing all designs and determining which will be the most effective at the job at hand, practically in the Earth's atmosphere and theoretically in a relatively lower gravity Mars atmosphere. The intricate topic of cost effectiveness will be kept in mind during this. Since this is just an early prototype, even when finished, our main focus is on producing the most effective collection and transport solution. However, in the grand scheme of things, these are meant to be present to allow for the construction of the base even before the first humans arrive on the Red Planet. As a result, we will attempt to make the rover operate fully autonomously to achieve this goal. On behalf of me, Tarun Bimanathan, and the rest of Team 6, thank you for watching our presentation.